Thank you for watching. This is a short video on how to use the Save on Trigger facility on the LA 1913-04B. The principle of operation is shown in this simplified flow diagram. The process is started by a trigger event. It can be a rising edge on the trigger input of the VNA, or a falling edge, or indeed it can be set to manual, in which case the user presses a button. Once the trigger event occurs, the VNA performs a sweep, and then it captures the data and saves it to local memory, and then the sequence is repeated until the right number of sweeps have been captured. Once we have all the data, we go to a display form, and in there we can choose in which format we display the data, and we can also reorder the data and save it to disk, or indeed we can decide to save all of the data to disk for later inspection. Okay, let's have a look at perhaps the simplest way of using the Save on Trigger. And here we have a setup to test a stepping attenuator. It's an electromechanical stepping attenuator, and here we have the driver box, and here we have the actual attenuator, and on the right we have the VNA. Okay, so let's look at the software, the user interface. Okay, so the first thing we are going to do is to set the trigger mode, and we're going to select manual, and we are now going to enable the Save on Trigger feature. So we tick this box here. When we do that for the first time, we get a dialog form asking us to enter the number of sweeps that we wish to capture. So for this very simple demonstration, let's select a value of 6. We click OK. And now we're ready to go. We can click on Start the Measurement. So once we do that, in order to get the VNA to perform a sweep, we have to click on this button here. So we click and it performs one sweep. We can now change the setting of the attenuator. I've done that, so we press trigger again and we can move on to the next, and so on. Okay, so we've now captured 6 sweeps and the instrument has stopped. We can now go and have a look at the measurements. If we go in the utilities menu here, we go to Save on Trigger, and here at the top it's saying that we've captured 6 waveforms and our target was 6. So we can go ahead and plot the waveforms. So let's select S21 here, and we click, if we just say we want to plot all the traces, and you can see there the various settings of the attenuator. We can plot the data for a single frequency by clicking on this box here and replot, and then you can see we see the attenuation levels at 1 gigahertz for the various settings that we recorded. and we can change the frequency. We can look at another frequency, say 5 gigahertz, and so on. We can also normalize the traces to one of the sweeps. So if we normalize to the first one, what happens is that the first sweep becomes our reference. It's all at 0 dBs, and then we can see the variation of the other settings relative to that first sweep. And you can see this is a nicely behaved attenuator. One thing you can do, which is quite useful, for example, is you can display the phase. If we just change the scale here, and then you can see how the insertion phase of the attenuator changes as you change the attenuation setting relative to the first one. Okay, so that was the simplest way of using the Save On trigger. We can now look at a slightly more exciting example. Okay, so here's what we're going to test. This is a digital attenuator. So we have an HMC 624 6-bit attenuator. It's a device that's rated to 6 gigahertz, but we're going to test it all the way to 8.5 gigahertz. And here on the left we have a very simple controller that sets the attenuator and then issues a trigger command to the VNA. Alright, so we now go back to the user interface, and the first thing we need to do is to change the target number of sweeps that we wish to capture. We know it is a 6-bit attenuator, but we're only going to measure 32 states. So the target number of sweeps is 32. We click apply and we go back. The next thing we need to do is to set the trigger mode. We want to set it to a rising edge, and that's all good. We're ready to go. And there we've captured 32 states. We can now see on the dialog form that we've captured 32. Our target was 32 and we're fine. We can, as before, display S21 to show you the data. And here's the first 16 sweeps, and you can see the various settings of the attenuator. You can add S11 if you want, and you can display the various values of S11. You've got to be careful, obviously, because the graphics starts to get very crowded. We can display the second lot from 16 to 32 sweeps, and those are the higher attenuation settings of the chip. We can illustrate as before the values at a single frequency, and if we just type all, we can see the various settings, the attenuation settings of the chip, right from the first to the last. And you can see that all those steps look quite well behaved, similar size steps. That's at 5 gigs. If we can look at 7, for example, then it's still quite well behaved, even though it's a 6 gigahertz chip. But if we look at 8, you will see that we have a step here, for example, that's not quite right, and another one here that's not quite right. So you can see that the chip is beginning to not perform because we're testing it beyond its specification, but it shows you how useful this tool is. And we can, as before, normalize to the first sweep and look at the face. And let's have a look. Let's do that plot. Okay, let's go expand the scale. And you can see the phase variation for the various settings from 1 to 16. We can look at the phase settings beyond the 16 by typing that in, and you can see how the phase varies. You can also save the data in various formats. There are 7 choices here. You can save and first and sort by parameters, in which case you will have one file for each S parameter, or you can plot all the sweep values for a single frequency, and you have a choice of which S parameters to save, of course. So it is really quite a versatile facility. All right, the other example I wanted to show you is how to control the VNA using the API. This is, for example, something that you may want to do in a production environment. And the advantage is that using the API, the measurement can be done a lot faster because there isn't the load of having to do the graphics. So in this slide here we have the basic arrangement. So we have a user application that uses the API, the DLL library, to control the VNA. Okay, so I'm going to show you a very simple user application. And here we have a user application. First of all, it has a function to find the VNA and open the communication channel with it. Secondly, this additional button here loads a calibration, and it's a calibration that will be able to measure the digital attenuator we've been testing. And finally here we have a button to start the save on trigger measurements. The variable that we can enter here is the number of sweeps we wish to capture. And to demonstrate the speed, the application sets the bandwidth of the VNA to its maximum of 140 kilohertz. So okay, let's go ahead and see how it works. So we press on this button here, and it will find the VNA. It's telling us that it's found a VNA with the serial number of 9040. And it's automatically loaded calibration kits. This is, of course, up to the user. In this example, we've hard-coded the calibration kits to be loaded. We now press this key, this button here, and that loads the calibration. We have a 201 point calibration from 300 kilohertz to 8.5 gigahertz, and it's been loaded with a 10 kilohertz bandwidth. But ignore that, because once we press this button, the bandwidth of the VNA will be reset to 140 kilohertz. Okay, so the last thing we want to do is we want to say that we want to capture 32 sweeps. So we type in 32 there, and we're ready to go. Once we press that button, the 32 sweep measurements will be carried out, and then the software will bring up the dialog form to look at the data we've captured. So let's do that. I'm going to click now. Okay, so it's telling us that we've completed the task in 1.7 seconds. So that is, we've performed 32 sweeps of 201 points each. So that's 6,400 frequency points that we've measured. And at each frequency point we've measured 4 S parameters. And that's all been done in 1.7 seconds. And that includes transmission of data from the instrument to the PC, and also error correction. And here is the dialog form that's telling us that we've captured 32 waveforms. And we, again, as before, we can display the first 16 sweeps. We can display S12 if we wish, and this is a symmetrical device, so it's the same information. And we can display S22, for example. So there you go. It shows how we can use the Save on Trigger facility through the API, and it demonstrates how fast the instrument can take measurements, which is ideal for a production environment. Thank you for watching.